looked at so far, at least in terms of the beam design we've been working on in the last, I guess we started last week right after break. We've been looking at nothing more than pure bending. Whatever type of loads we might have, whether they're distributed or not. However, at certain places, and it doesn't matter where, because this does happen everywhere, we've got not just the bending, but also, as we know, we've got shear across the face of that beam. Last week we took our first looks at how to design the cross section to best resist the bending, but we're going to look a little bit more at the shear. However, we're going to take it's not an obvious change here, I think. In fact, this is the 7th time I've taught it, and every time I teach it and I sit down and review my notes and I look at this and I think, gee whiz, I'm just amazed where this comes from that we're looking at. We're not going to look just at this cross-sectional shear. All we need there to resist the cross-sectional shear, the transverse shear, is we just need enough area, because we know that the shear stress is equal to that shear divided by an area. We don't need anything like we did with the bending, where the normal stress was a factor of the size and shape of that cross-section. Remember that the C had to do with the size of it, and the I had to do with the actual shape, the moment of inertia. Basically what we are finding out from there is that whatever the cross-section, we needed as much area away from the neutral axis as was practical. And that's why I-beams are so very useful in construction purposes, because they have a very, very big I, because of so much of this area that's away from the neutral axis. But the weight wouldn't be any greater than a beam that would be much smaller. If those two had the same area, they'd have the same weight. But this one has a much greater I, and thus a much greater resistance to bending stresses. Now we're going to look a little bit at these transverse stresses and the trouble they cause. However, what it turns out to be for us is it's not the transverse shear itself that we need to work with, because, as I said, that's easy to handle. We just need enough area. As long as we've got enough area, we can withstand the transverse shear. What we have to look at is the fact that as beams bend and are subject to some kind of transverse shear, and it's very easy to see with a cantilever model, if the beam has no longitudinal resistance. Imagine we had this beam made up of many, many layers. Could be like a piece of plywood, but I'm thinking more like some very, very thin, maybe veneer pieces of wood just stacked together and not even bonded to each other. If we apply this kind of load, then there's going to be a lot of bending, because each of these sheets can slip past each other, and of course this is a greatly exaggerated picture, as we often have to do. Whereas if we took those very, very same sheets, and this is just what plywood does, and bonded them together so that they actually stuck to each other, and imagine we do that, we can very simply do it. Imagine we put some kind of I don't know what to call it, some kind of thing there, that's a good word, thing, some kind of thing there that keeps those, keeps the sheets from slipping past each other as happened here. When that happens, we get a very much better resistance to the bending. And it's quite easily demonstrated with a simple textbook. If I let the sheets slide past each other, which is this kind of picture, then there's almost no resistance to bending. This is sticking up just because it's stiffer. But you can see if this was our beam and we allow the sheets to each slip past each other, it has almost no resistance to bending at all. But if I put this on here to do nothing more than hold the ends in place, which is this kind of, I think I called it a thing, then it does much better in resisting bending. Remember before it slumped all the way down here. The idea you can get though is if we can even do better with these in here, maybe if I move these things to the side so there's less slipping all the way around. It does even better. So what we see is that those loads, like these and like these, that cause cross-sectional transverse shear also give us some kind of trouble that we need to address of this longitudinal shear along there. We need to address how to keep the fibers of the beam, and it's especially true with a wood beam that is truly made of fibers. It's the rings of the tree growth that actually make up layers in a beam like that. If we don't address the ability of the beam to withstand those kind of shears, then we're also going to have greater deformational failure. We might not have material failure, but we clearly get a beam failure there that is not going to be a good design. We have to address that as well. So that's what we're going to look at now as we take a peek at these things. So we've seen at least part of it before. If we look at some elemental piece of a beam in any kind of bending, we know that that has the transverse shear that we've been looking at anyway. We'll put it in terms of shear stress rather than in terms of the shear itself, because it does have to do with the area. But we're now going to look at these longitudinal shear stresses that run down the length of the beam in the axial direction. So here's our setup for this. As usual, what we're going to do is look at an elemental piece and how the forces stack up along that, and then expand that out, if you will, to the entire beam. So here's a chunk of the beam just taken out there. Axial direction. So that's the X direction. Across the interface, that's also going to be our neutral axis. So we'll give it some kind of prismatic cross-section. Remember what a prismatic beam is? What our term prismatic means?
I believe you were referring to a symmetry along one of the axes.
Symmetry with respect to the y-axis. X-axis is our longitudinal length down the length of the beam. Our y-axis is typically up from that. So just some prismatic cross-section. whether it's an I-beam or a circular beam like a tube or a rod would be, or even just a simple square beam, it doesn't matter, because there is y-axis symmetry. It's the cross-section is mirrored across the y-axis. All right, so the shape of that is not of material interest yet. And so we'll look at some elemental piece right there with the flush with the top and some little bit of distance down. And remember then our reference values, the distance from the neutral axis to the greatest extent of the beam in the y direction is c. We'll call this distance here y1. And what we're interested in is the shear along this bottom face, which is going to be all the way across the beam, across the bottom of that little piece there. So that's our setup. And we'll call this area A. Give it a big fat script A. It's always fun to draw new symbols and get your own style with them. So that's what we're going to call that one, kind of a script A. I think the book calls it A prime. I'm not real fond of using primes because they look too much like exponents, but I think that's what the book uses. But it doesn't matter. We're going to be done with that in a little bit. So we've got this. Now if we look at it in perspective, we've got this little piece here that runs all the way across the beam. And that's the elemental piece we're interested in. We don't need to look at an elemental piece in the z direction because it's symmetric in the z direction, because it's the same over here as it is over here because of the symmetry about the y-axis. So we only need to look at this little piece, delta x wide, and not too concerned with the width in the other direction because it's a square piece. So we've got this piece that's delta x wide, takes up a whole area dA. We're kind of mixing d's and deltas, but as usual, we're going to be done with those very shortly, so we're not going to worry too much about it. And so let's look at the loads that we have on here. Perhaps there's some kind of distributed load across the top, or it could be a point load. It doesn't matter which. We take care of all of those things as we look at them. And in terms of the force, this is W. Remember, that's the size of the distributed load per unit length, but the unit length here is delta x. So that's the entire load force on that piece there. We also have, of course, shear. So this we'll call V, and that's also V, but they're on slightly different sides, so we'll call this side, we'll call this C. Let me get the same notation so I don't drop it later. Oops. We'll call this CD, and this is C prime, D prime, just to designate those sides and corners and the like as we need them for reference. So that'll be VD. The shear on the D face. This is the shear on the C face. And then we also have the normal stresses. And remember, those are linearly distributed from the neutral axis. So however down far that is. So we have those on one side. I'll call that, that's the normal stress on the D face times the area over which it's acting, dA. And we have the same kind of thing over here. Hope you started your drawing big, because even mine's getting crowded. So that's on the C face and the area over which it acts, and that's also again down to the neutral axis. And then we've got one last little piece of it, and that's this longitudinal shear that we need to investigate now. We'll call that delta H. God only knows where that came from, but we've got that there. So we'll sum the forces in the x direction, and because of our static limitation, they'll sum to 0. So let's see, we've got delta H, this new piece we're looking for, the longitudinal shear. Yeah, David?
Well, you'll be needing longitudinal shear on top.
No, because we're actually at the top of the beam, so there's nothing there.
Okay, just want to make sure.
We're looking at the internal shear. And then what else is in the x direction? Well, it's these two shear stresses. So integrating over that whole area A, this whole cross-sectional piece there, it's what, sigma C minus sigma D dA. All right, I think we're okay, and that's got to equal 0. Okay, we can change things up a little bit, because this part here, remember that sigma equals minus my over I. The normal stress at any place is a function of the bending load M, the position across the interface, and the cross-sectional moment of inertia. So this is for the entire cross-section here, that I. But that's what we established last week, so that's nothing new. But we can put that in here so that now this all becomes, we can now solve for this delta H. Delta H equals MD minus MC over I, because those are constants, they can come out. This M is the moment at the D face, C is the moment at the C face, and I. Those are all constants, they come out, and we're left with just the integral over this exposed area above our plane of interest, as established by Y. So I think that gives us all the pieces we need. And this little part here is entirely geometry of the cross-sectional piece above our plane of interest. So this is the first moment of area above the plane we're interested in, as established by this Y here that we're doing right there, right across here. And so we can look at that at any place that we need to, depending on how far away we go, whatever that cross-sectional area happens to be. We're going to call this capital Q. And for our nice regular solids, it's nothing more than Y bar A above the plane. Now, the reason, the way this becomes of interest, and we'll do a problem very much like this, is imagine we have an I-beam we want to make out of 3 wood planks. You've got a whole bunch of 2x6s or something, and you want to make an I-beam out of them. So you'd put them like that. You'd be very, very concerned with how you're going to attach these to each other so that they don't come apart at those interface planes where those these cross-section, these beams are joining each other. So maybe you'd put nails through there. You might also put adhesive all the way along that face as you put these together. And it's this very shear, longitudinal shear here, that's trying to pull the beams apart at those places. If loaded, that you wouldn't want the beam to do what we showed it doing with the earlier illustration. You wouldn't want these planes shifting off of each other, which is why you can glue them and screw them to make sure they fit. Make sure they stay in direct and intimate contact to maintain the integrity of the beam. So we're almost done with this. We almost have it put together. So this becomes delta M over I, where delta M is just the difference in the moment on either side, times Q. Now we're almost done with all the pieces we need. So let's see what we've got. So we've got, I'm just rewriting that same thing, delta M over I times Q. Now we're going to grab something from a little bit in the past. Remember, this delta M is the difference in moment on either side. It's not in this picture because we did a force balance, not a moment balance. We're going to add to this our relationship between the moment and the shear. That's from our shear moment diagrams. We'll macroscopically look at it a little bit, where instead of the differential values we'll use the deltas, because that's what we've already got here. So delta M can come out and be replaced with V delta X. So we get V Q over I delta X, where remember delta X is how much in the X direction of this piece we're looking at. And so I think, yeah, so we're real close to what we need. Now we have the shear per unit length is the transverse shear Remember, this is the longitudinal shear over here is delta H. This is the transverse shear that we've been calculating since all the way back into midway through our statics class, not even midway, about a third of the way into statics last fall, we came up with this transverse shear. Q, remember, is the first moment of area of the section above our plane of interest. And then I is the moment of inertia of the entire cross-sectional area, the entire face. So that's as tricky as anything for this, is those two pieces. So now we can determine what the shear is per unit length. The way we'd use that is if you were going to nail these, you'd put nails every couple inches, and it's easy to use that as our distance delta x. So we can figure out how much shear there's going to be per nail, and then we can make sure we got nails with enough thickness and area that they can withstand that. So we'll do that very problem as an illustrative example of what we need to, how we work with this. All right, so here's a beam you're going to build this summer for your parents' deck, made out of 3 planks, nailed together, dimensions 20 millimeters. Each plank's exactly the same. Each plank's 20 by 100 millimeters. So of course this is a cross section. We take a second to make it look like a very realistic beam. It doesn't look anything like that at all. All right, so there's our beam in cross section, and then we want to find the shearing force in each nail, expecting to put them at approximately 1-inch intervals. We'll put them at 25 millimeter spacing between each nail. So that's our delta x that we're looking at, the spacing between each nail. We want to find the shear force in each nail with a calculated shear, usually the maximum shear of, let's say, 500 newtons. We would find that just like we would have found it last fall. We look at the beam and see how it's loaded, figure out what the reactions are, and then figure out what the shear moment diagrams look like. See what the maximum shear is, and then build the beam to resist that maximum shear. Because we've seen now that it determines what the cross-sectional area is. All right, so our beam in cross-section looks like that, and we're worried about the nails withstanding the shear at that interface there where the two planks are put together. We don't need to do the other side because it's symmetric about the z-axis. So we don't need to figure out where the neutral axis is by symmetry. We know it's right down the middle because it's symmetric not only about the y-axis but also about the z-axis. So we've got all the little pieces we need. All right, so we've got the shear we need the Q, the first moment of area, with respect to the neutral axis of the part above the plane of interest, which is this entire area there. Not just the part of area directly above the intersection of those two planes, but the entire area all the way across. So that's our A. So we need the first moment of area of that. Then we also need the first moment of area of the entire cross-section. All right, so Q, and remember this is of A, is nice simple shape. We don't need to actually do the integral. We just need to figure out what it is. And so let's see, if that's right in the middle, then this is 50 millimeters up to there, and then another 10 up to the middle point of the beam. So this is 60 millimeters. That's Y bar. And then times the area of that entire piece, which is 20 by 100. That's the area of A, and that just comes out to be 120,000 cubic millimeters. It's not a, well, I guess it is a volume in a way. Not real sure what's the volume of, but there you go. All right, other piece we need is the moment of inertia of the entire cross-section. And that's the central moment of each piece plus the parallel axis theorem as applied. So let's see, this is 1/12, 20 by 100 cubed. So that's 1/12 BH cubed for the web here. That's what that piece is called. So this is I of just the web. And then the other pieces are the centroidal moment of inertia of the flange, which is 1/12 B, which is now the 100 dimension, H cubed, which is the 20. That's the centroidal moment of inertia of the flange. Plus AD squared, which is 20 by 100. Running out of space. So I'm continuing this square bracket here. Plus 20 by 100. That's A. And then D squared is, well, it's again the 60 that we had before. So that's AD squared for the flange. Except there's 2 of them. So we just multiply that square bracket by 2. There's 2 flanges. So there's the moment of inertia of the web, which happens to sit right on the neutral axis anyway, so we don't need the parallel axis theorem on that. And then the moment of inertia of the flange times the parallel axis theorem times 2, because there's 2 flanges. That comes out to be 16.2 times 10 to the minus 6 meters. To the 4th. So now we have all the pieces. Well, now we'll be able to find the shear per unit length. Then we'll put in the fact that we have 1 nail. So, oh, by the way, this is often given the symbol little q, also known as the shear flow, because it's as if that's the amount of shear that's flowing down the cross section there as we look at it. So we want to find out how much shear there is per nail. So we figure out that Q, the Q we've got, big Q, we've got I, we've now got just multiplied by delta X, which is the distance between each nail. And that comes out to be, let's see, 500 newtons times Q, which is up there in millimeters, but make it into meters. Meters cubed. That's Q over I, which is 16.2 times 10 to the minus 6 meters to the 4th. So let's see, what units do we get then? We get newtons per meter. So the amount of shear, longitudinal shear, remember shear down the length of this face per unit meter, but we only want to do it for every nail, which is, each nail is 25 millimeters apart. So we put that in as our delta X unit length. We get 93 newtons per nail. And now we can make sure we've got nails that are of such a material and such a cross-sectional area that they can withstand the shear stress. All right, so the calculations aren't really very complicated. You just have to be careful that the Q, the first moment of area, is based upon this bit that's above the plane of interest, and that the I you use in the equation is for the entire cross-section itself. That's really about the only places where students tend to make some mistakes. All right, remember that's the shear. The longitudinal shear in that plane. But to see what it is in terms of the shear stress, we need to look at a fairly similar picture as we've been looking at before. So here's the beam in cross from the side with some kind of cross section to it. Whatever it might look like doesn't really matter. The idea is all the same. So we're now looking at this this delta H across some piece there, which will look like this. Where the part that's resisting that shear, so we can find out the shear stress, is this bit there right on that face there. That's where the shear resides, is along the bottom face of that little trapezoidal piece. Looks something like that. So this then becomes the average shear stress is the delta H over whatever that area is, which is T delta X. So this is VQ over I T delta X is the average shear stress. Oh wait, I forgot this delta X here. So there's actually two delta X's. Good, because they cancel. So we get the average shear stress, which is about equal to the tau xy that we were looking at so many weeks ago. Across the cross section like that. All right, just to be accurate, let's see. If we look at the beam from above, so now the z-axis is coming out like that, x-axis down there, the y-axis right at us. This distribution of this shear stress is something like that. And what we're looking at is the average shear stress. And so we are underestimating it a little bit because there is a maximum shear stress down the center in the center region. And we're underestimating that a little bit. And for rectangular cross sections, the book shows that maximum shear stress, for non-rectangular it's a little different, but it comes out very easy for nice rectangular cross sections. And that's, by the way, that A is the cross-sectional area of the entire piece. Okay, so let's run through it again with another example. A lot of little pieces had to come together, but as usual, a whole bunch of the little pieces dropped out, and we're left with just one or two big working ideas. So let's figure out what we've got. Let's do a problem or start to finish and see what we've got. So we've got a beam simply supported little bit of an end sticking out there and a distributed load up to that point. Kind of looks like a diving board. 400 pounds per foot. So evidently we've got the entire youth group on the diving board. 400 pounds per foot. And one brave kid out on the end there happens to weigh 4.5 kips. Big kid, football player. 8 feet and 4 feet are the dimensions. And the cross section is simple rectangle, 3.5 inches in width, but of unknown height. In fact, we're going to have to design for that. So we've got maybe some wooden beam like that. We've got 3.5 inch thick boards, but we can order them to any height we need. Meeting these design restrictions. Allowable shear stress of 0.250 KSI and allowable normal stress of 1.75. So we're getting more capability now of designing a good cross section because we can deal with it not only in terms of bending, but in terms of longitudinal shear as well. Okay, so we need to know what the maximum shear is to avoid that trouble. We need to know what the maximum moment is to avoid that trouble. So the shear moment diagram is pretty easy to draw. We can do them real quick. The reaction, the first reaction there is 0.65 kips. So we start from there. And then we have this uniform load, so we know the shear has that very same slope. Takes us down to a point of 0.385 kip. So, as we might expect, there's a worry about shear failure there. And then the reaction at the roller is 8.35, so it jumps up by that much. It jumps up to about 4.5 kip. So that's our worst case shear there then. So there's our shear diagram. In terms of the maximum moment, all we need to really worry about is what are those areas, because remember that's delta M, and we have 0 moment here because that's pinned, we have 0 moment there because that's free, so whatever one of these is the greatest delta moment will be the worst case thing. That area turns out to be -18, and this area turns out to be +18 because it comes to 0. So we know that our maximum moment is 18 and it's right at the roller. Exactly what the shape of the moment curve is on either side isn't really of concern here, because what we need is to make sure that the beam resists the maximum moment, which we can now figure out. At least in terms of h. Remember, h is unknown. So this comes out to be, let's see, we know that allowable normal stress. The moment is 18 kip feet. C is 1/2 h. Remember, h is unknown, but we'll be able to solve for it here. And the moment of inertia is 1/12 b, which is 3.5. over 12 feet, and then times h cubed, which we don't know what it is, but we do have a value for this. So we can solve for an h, the height of the beam we need to resist bending failure, and then we'll go back and check and see if that's adequate for the shear failure, longitudinal shear failure. So that h becomes 14.6 inches. So we need a beam to resist the bending failure of at least 14.6, but now we'll check the allowable shear stress and see if we're okay with that. And that's 3v over 2a. And we've got the shear, the maximum shear is the 4.5. Over 2. And the A, we now have at least a design area. We're checking now to see if it's adequate. So we divide by the area we've now picked for design to resist the bending failure, checking it now for longitudinal shear failure, and this comes out to be 0.33, no, sorry, 133. Kips per square inch, and that is less than our allowable limit, so that h of 14.6 is adequate. It will protect in both bending failure and longitudinal shear failure. Speaking of which, for wood beams, when a wood beam does fail longitudinally because of whatever the loads might be, it's interesting the way it fails. If you look at it in, it tends to fail something like that right down the planes where this longitudinal shear was the greatest. It actually does pull the planes apart, and then the bending separates them even farther. I think there might be a picture in the book on that, so you can double check it. All right, before we do another example, just to make sure that you understand what the Q is that we need. For the wood beam, we had the wood I-beam. the concern was right at this place, that plane there, and so we needed the entire area above that plane. If we were making this out of steel plates and we're welding them, we'd run the welds down there, and it's still essentially the same area, because we're still concerned with the area above that plane. If we're taking cast I-beams that are already one piece, most steel I-beams are not made up of separate pieces welded together, they're cast this way. If we needed to strengthen that for some reason by putting some kind of channel over that, which is not uncommon, I guess. So we want to rivet maybe through those places there as we attach this channel beam to the top. Now this area, the plane of concern is this one here, and the area beyond that is this entire area of the channel. Even though some of the channel actually hangs below that plane, it's not available right at the plane. We have to take in the whole area to account for this longitudinal shear down the whole piece. So that's not as obvious as it might be for some of these other ones. And if we were, say, making a box beam out of a couple boards nailed together, as you might do if here in the Adirondacks, it's nice to have wood as a big part of construction, and so you might want nails through there. So the planes of interest then are these planes here where the longitudinal shear could shear through the nails. So the area we use for that is then the area of that piece in the middle there between those two planes. So sometimes these areas are a little bit difficult to determine, so we're gonna avoid overly complex ones and do ones that are a little bit more obvious so we can make sure it works. Okay, so here's one for you to do. As usual, I'm working way too hard. So here's one for you to look at. Have a beam. Well, let's not worry about the whole thing. We don't need to find the reactions and all that. Let's just take a look at it in one place. So we'll look at it there. We know that the reaction here is 15 kilonewtons. And so we know that the shear across that face is also 15 kilonewtons. And the cross section is something like this, sort of a modified I-beam. A University of Tennessee beam, maybe that's what it is. 100 millimeters. $20 millimeters there. 80 down the web. 20 on that little bottom flange. And 60 across the bottom of the T. want to find at two places. We want to find the shear there and there. So we'll call those two places A and B. Find the shear, the average shear stress. And that's that delta H thing we've been looking for at A and B. All right, so you're going to need the moment of inertia of the beam. I'll give that to you, and I'll give you where the neutral axis is, so you don't have to find those. You can just use the you can work on the new part today. So the moment of inertia of this beam comes out to be 8.63 times 10 to the minus 6. 68.3. With the neutral axis, 68.3 millimeters up from the bottom. So normally in a problem you'd have to find those, but I'll save you the trouble and just double check that you can find the average shear stress, the new part of what we're working on then today. All right. Everybody got the picture? All right. So you need to find the average shear stress at a piece where the the transverse shear is 15 kilonewtons, and we have a beam with that kind of cross section. Then check the two spots of interest, the two planes of interest. Two different calculations. Basically what you need to find is that Q, that capital Q. The first moment of area of the area beyond the plane that we're looking for. Those are the two parts you need. Most of the other two parts are, or the other parts, I and V and T are the same for either calculation. Just to make sure, if nothing else, you can find what Q is for this beam. I don't know you, Tommy. Maybe you'd love to integrate. Most students will avoid it if they can. Remember, this is Y bar A for the appropriate area that I've been cross-hatching in red, the area above the plane of interest, beyond the plane of interest from the neutral axis. Got V, got I. T, I hope, is pretty obvious. It's the width of that line. Did I give that to you? And I didn't specifically give it to you. It's 20 as well. Hard to get all those things in there sometimes. Make sure your unit's okay. I think you lost a order of magnitude. I think you're getting the same thing here, so maybe I will double check. Okay, now got it. Watch your units on Q. Y bar for A is from the neutral axis up to this midpoint there, Y bar A, which is the full 120 minus 68.3 minus 10 as we come down to it. 41.7. Does that sound right? And then the area of A, what did you use? Phil, what did you use for the area here to find QA?
Oh, just 100 millimeters times 20.
It's this area here. 100 times and should have gotten 83.4 times 10 to the minus 6. Watch your units. I got a bunch of them in there, but in the end, you got to work them out to one spot. 83.4. Is that right? Chris, you're looking shocked and amazed. That we agree? That amazes you?
Striking my drink.
That amazes you. Alright, so now we can find the average. Because we've got all the pieces now. The shear was 15 kilonewtons. Q, 83.4 times 10 to the minus 6 meters cubed. I gave you 8.63 times 10 to the minus 6 meters to the fourth. And T, what'd you use for T? You have that, Tom? The 20 millimeters, the Z dimension of the interface of interest, by putting it in meters. So we get kilonewton meters squared, as we should for average shear stress. Okay. And I have written down 725 kilopascals. That's an order of magnitude off from what you have. You have 7.25 megapascals. Okay. Well, it's just multiplication now, whatever it comes out to be. You got the same orders of magnitude on everything up there? 83.4 and 8.63. Oh, 2 meters, yeah. Oh, I see what the difference is. Yeah, okay, I just wasn't looking, yeah. Yeah, you're right, what I had in my notes was 1.5 kilonewtons. I just missed the decimal place on my notes. So your answer's right. David, you got that?
I'm still trying to work on some of your theories, because there was one I didn't get any answer as to how it was figured out.
I believe that was the maximum shear stress was equal to,
3V over 2A?
Yes.
Yeah, remember that's for a rectangular beam only. And that's where all the simple parts, when you just have a rectangular beam, a whole bunch of things get very much easier, and a bunch of B's cancel, a bunch of H's cancel. The book lays that out, but that's a rectangular beam only. And we're not working with one of those here. And it does not apply to a rectangular portion thereof. The entire beam has to be rectangular to use that 3V over 2A. All right, so let's check the other two pieces. And then I'll throw up another problem for you, and you can double check it when you get back on Friday. So for Q, B, you got what number? Travis?
69.96 times 10 to the minus 6 meters.
Okay, yeah. 70 times 10 to the minus 6 meters cubed should be sufficient. And then the average shear stress then at that point, you guys would have gotten, what, like 6.08 megapascals, give or take a little bit. 6.1 megapascals. Chris, you got that too? Phil, you did? Okay. All right, let me set up a problem for you. You can look at over Friday. I know you wouldn't dare come back without having that completed. Right, Tom? All right, a beam made out of 3 planks. Where it's 2 side boards joined to one intermediate board. You do this if you were using this as a structural as well as a decorative beam of some kind. It's nice to have the full side piece and not showing any of the joint there. So then with nails stuck through. So a cross section looks something like this with nails through there. All right, given dimensions. 250 millimeters on the inside, 150 on the side. 30 the thickness of that board, same for the top board. Spacing between the nails. .100 millimeters. And an expected maximum shear of 800 kilonewtons. Sorry, 800 newtons. Yeah, for a wood beam, 800 kilonewtons is pretty high. So expected shear of each nail has a diameter of 2 millimeters, so find the average shear stress in each nail. All right, find that. Let's see, make sure you got all the pieces there. All right. Okay, average shear stress in each nail, just like we did over there, VQ over IT. So you're going to need to find the cross-sectional moment of inertia, which means you're going to need to find the neutral axis. Obviously, it's going to be somewhere up near the top, but you need to find where so that you can find the cross-sectional moment of inertia. Then you also need to find Q for the appropriate area, which, as I showed you with the box beam, this is the same, just doesn't have the bottom to it, is that area there between the 2 planes. We don't use the bit of the side because that's not supporting any of the shear that's going across those spaces where the nails are. All right, then with all that, you can find the shear stress per, average shear stress per nail. Okay, so that's the problem set. And you won't even dare walk in the door on Friday without that being done. I know you guys. Travis, you're smiling because you're anticipating the fun of coming in with it done and shutting me up for once. All right. That's a wrap.